Hello everyone, it's Dr. C. In this video I'd like to talk about constant pressure calorimetry. And we also call that coffee cup calorimetry, as you will see in just a minute. But this is an experimental technique where we can measure the heat flow of a reaction or of a system. So we can determine whether something's exothermic, endothermic, how much the temperature might change if we do this reaction, and so on. So a key term here as we move forward is specific heat. All right? And we label that C sub S. And so let's look at what this is. It's the amount of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius. Okay? So the units we're looking at for specific heat are joules per gram degrees Celsius. Okay? It's the amount of heat, energy in joules, to raise the temperature of 1 gram of substance 1 degree Celsius. Okay? That's going to be very important because the specific heat of different substances, as you'd expect, is different. Water, for example, has a very high specific heat, and that is an important property of water. And then we're going to look at some different metals here in just a minute, and their specific heats vary from one to the next. So why don't we just look at that so you can see some of these values. So here's a table, and again note the units, joules per gram degrees Celsius. This asterisk is just saying that these are typically measured at 298 Kelvin. Okay, and so you can see, the metals that are shown here, lead at 0.128 all the way to aluminum at 0.9. Okay, so that's probably about a 7-fold difference in those specific heats. Look at the specific heat of water, all the way up at 4.18. That means that there can be a lot of energy can be stored in water. And think about that when we use water a lot to cook our food. All right, boil our pasta or whatever. Right, when we put energy into that water, we've stored a lot of energy in that water, which can then be used to cook our food. Because every 1 gram, 4.18 joules is stored for every gram of water when it's raised 1 degree Celsius. Okay, so high specific heat. And here's just a few other materials in case you might be interested: glass, granite, sand. Okay, so we'll see how we use that, because when we do reactions, the specific heat of the substances will come into play. So let's look at what a coffee cup calorimeter is, a constant pressure calorimeter. So it's constant pressure because it's exposed to atmospheric pressure. Right? And using a styrofoam coffee cup, particularly if you nest 2 of those together, actually is a pretty darn good insulator and works pretty well to hold any heat of reaction inside that calorimeter. And so look at what we have. We have a thermometer, so the reaction takes place inside that calorimeter. If it's exothermic, the temperature will go up, and we'll measure how much the temperature changes. We'll typically have a way to stir the reaction mixture so that the reaction is uniform and the heat is released well. And we want to cover it as well. We want to cover the container so heat doesn't escape to the surroundings. All right? Very, very simple experimental apparatus, but it works surprisingly well in say a general chemistry laboratory for how simple it is. All right, so let's look at how we would actually calculate the amount of heat that is absorbed by a substance or released by a substance. And here we're just focusing on, at first, just one substance. The next, we're going to do a calculation with one substance, and then we're going to do a calculation where we bring 2 substances together and take a look at that. So, very simple equation where Q stands for heat at constant pressure. M is the mass of the substance. All right, because that will come into play, because remember, specific heat, which is the next quantity in that equation, is dependent on the mass. It's the energy needed to raise the 1 gram of substance, 1 degree Celsius. So we need to factor in the mass. Of course, we also need the temperature change. Okay, delta T, and delta is going to be T final minus T initial. Okay, so clearly if we, for example, add a certain amount of heat to an object to raise its temperature, we could measure that temperature change. We look at the mass of the substance, specific heat, and so on. Okay, so pretty simple equation. So let's just look at a quick example here. So how much heat must be absorbed by 1 liter of water? Okay, so let's highlight some of the important quantities here. 1 liter of water to raise its temperature from 25 Celsius to 100 degrees Celsius. And the density of water is 1 gram per milliliter. All right, so we want to calculate the amount of heat absorbed by that water. All right, so we need to know the mass of the water, we need to know its specific heat capacity, and we need to know the change in temperature. All right, all those will factor in. Is the mass given? Not directly, but we know the volume. And the density of water is about 1 gram per milliliter. Well, 1 liter, you should know, 1 liter is 1,000 milliliters. And if water is 1 gram per milliliter as a density, that means we have 1,000 grams of water. So we do know the mass. Specific heat of water we would look up, we just saw it in that previous table, 4.18 joule per gram degree Celsius. And delta T, T final minus T initial. T initial, 25 Celsius, we're raising it to a final temperature of 100 degrees Celsius. All right, so very quick calculation. Mass, 1,000 grams. Specific heat, 4.18 joules per gram degree Celsius. And delta T, T final, 100 degrees C minus 75 degrees C. Okay, sorry about that. These kind of ran together. All right, so let's see what we get. Oh, sorry, this is 25. I was in my head, I was getting the answer for the delta. So it's 100 minus 25, which is 75. So that's why I wrote 75 there. Sorry about that. Okay, so 75 degrees Celsius is our delta times 4.18 times 1,000. And I believe we have 3 sig figs using 4.18, our 1.00. Temperature might only be 2, but let's go ahead and call this 3 sig figs for now. 3.14 times 10 to the 5th. And what would our units be? Yeah, grams cancel. Degrees Celsius, so our delta is going to be in degrees Celsius, which will cancel with that degrees Celsius. And as you'd expect, for the amount of heat absorbed, it should be a unit of energy, and the unit of energy is joules. Okay. There you go. So that's just the amount of heat we had to put into, had to be absorbed by the water to raise that 1,000 grams of water from 25 Celsius to 100 degrees Celsius. Now, one more point with this before we go on to another problem. Note that it came out to be positive. To raise the temperature of a substance, we have to add heat. Okay? It's endothermic. Okay? Now, this really isn't a reaction, but we are having to take energy, heat, from the surroundings into that system, the water, to raise its temperature, endothermic. All right, so that type of calculation is relatively straightforward, because we're just looking at one substance. All right, now let's look at an example that's a little bit more difficult. Okay, because we are going to look at 2 substances. We're going to look at a substance at a higher temperature, and we're going to add that to a substance at a lower temperature. So what's going to happen when we bring a hotter object in contact with a colder object? Yeah, we're going to have heat flow. Thermal energy is going to go from the hotter object to the colder object. That energy of motion. Okay, the hotter object, the molecules are moving faster. The colder object, the molecules are moving slower, and that energy will be transferred over till they'll reach the same thermal energy. They'll reach the same temperature at a certain point. Okay, so what we're going to assume is that one substance is going to lose heat, and that's going to be the hotter object. Okay, and then the other substance is going to gain that heat. Now we're going to assume for this calculation, we're going to make a big assumption here, that no energy is lost to the surroundings. Okay, all the heat lost by the warmer object is going to be gained by the cooler object. No heat lost anywhere else. No heat gained by the calorimeter. Okay, that's a relatively good assumption. We could make this calculation a little bit more complicated by adding in the heat capacity of the calorimeter, but let's not do that because the heat capacity of the calorimeter is going to be relatively small. This will give us a pretty good approximation. Okay, so this is the key concept here. When we bring a warmer object into contact with a cooler object, clearly the warmer object is going to lose thermal energy, the cooler object is going to gain that, and we're going to assume that all the heat lost by the warmer object is gained by the cooler object. No energy lost anywhere else. Now, how do we represent that heat? Well, we call it Q now. We're calling it, that's the heat at constant pressure, and we give it the symbol Q. Notice the sign here. The colder object, the water in this case, is going to gain thermal energy, gain heat. Okay, technically not the correct way to say gain heat, but we'll go with that. And then, okay, we have a negative sign for the metal. That's going to lose thermal energy, lose heat. Okay, so that's how we're going to have to set this up. Hot object, cold object, heat transferred from the hot object to the cold object, and we know how to calculate that heat, that Q. But one is gaining, the cold object, one is losing, the hot object. So you have to have your sign convention there. You have to have the sign convention. Well, think back to that last problem. How did we calculate Q? Oh yeah, right? Mass, specific heat, and delta T. So we can now write, I'm going to write it over here to the side, we can say mass, I'm going to use W for water right now, mass of water, specific heat capacity of water, delta T of water, right? And that's this Q right there. And then the metal is losing heat, and so that's a negative again, but we would need the mass of the metal, specific heat of the metal, and delta T of the metal. There you go. Now this is a little bit more complicated because we have that MC delta T on either side of the equation. And also note you have to have a negative sign on one side of the equation. All right, so let's look at what we have. We know the mass of the metal. We know its initial temperature. Okay. We actually want to calculate the final temperature of that mixture. Now the mixture is the metal and the water together. They're going to come to the same final temperature. They'll have the same T final. That's what we want to solve for. All right. Specific heat of the metal, do we know it? It's not given. Oh yeah, we can look it up. Let's go back. I think copper is 0.329 or something like that. Let's see if it's on our list here. 0.385, I'm sorry. Okay, 0.385. All right, so let's write that down. So for, and I'm going to go down lower on the page, but let's just write this out. We know the mass of the metal is 20 grams. Put our negative sign there. Okay, specific heat, we just looked up, 0.385. And delta T. Now, you'll see it's degrees Celsius, but the delta in Kelvin is going to be the same. Okay, our starting point is just different, right? 0 degrees Celsius is 273 Kelvin, but 100 degrees Celsius is 373 Kelvin. It's the same 100 degrees between the freezing point and boiling point of water. So we can do delta in Kelvin. It's the same as degrees Celsius for the delta. Okay, so we can work with that. So T final minus T initial, which is 373 Kelvin. Okay. Now, since I'm plugging in Kelvin here, our T final is going to come out in Kelvin. That's no big deal. And let's look at water. 50 milliliters. Do we know the mass? Yeah, well, we kind of saw this in the last part. We can, the density is about 1 gram per milliliter. So we have about 50 grams of water. We use a specific heat of water in the last calculation, 4.18 joules per gram degree Celsius. T final is going to be the same as the other T final. And what's the T initial for water? 293 Kelvin. Sorry, I did not plan that out very well in terms of my space, so I'm going to write this again below. So let's get some more room here. So let's rewrite this. Try to be a little neater here. 50 grams of water, 4.18 joules per gram degree Celsius for the specific heat capacity. T final. Now again, we're going to let that hotter piece of metal sit in that colder water until the temperature on that thermometer stops changing. Okay, once it equilibrates, we're going to say, boom, there's our T final. Well, we're actually going to try to solve for it. If we ran the experiment, we'd actually measure the T final. Let's see if we can solve for it. Don't forget your negative sign. Okay. So you can see there are a lot of things there. A lot of different potential variables. But we're essentially given everything except T final. So now we have to do some algebra. That's all we've got to do. So let's go ahead and take 50 times 4.18 times T final. And that's going, let's see. That's going to give us 209 T final minus, so again, then we have to take 50 times 4.18 times a negative 293. And I got I'm going to carry some extra sig figs here. 61,237. Okay, now I have to do that on the other side of the equation. Now note the negative sign. So this is going to be negative 20 times 0.385 times T final. That's going to give us a negative 7.7 T final. And then negative times a negative here in a positive quantity. I get 2,872.1. All right, almost there. So now we need to get T finals on one side of the equation, get our constants on the other. Let's go ahead and first add 7.7 T final to both sides of the equation. And then we're going to subtract, let's see, and then we're going to add, actually, let's add 61,237 to each side. That'll cancel out there. Let's see what that gives us. So we end up with 216.7 T final is equal to 64,109.1 divide by 216.7 T final now I think we really only had 3 significant figures. Let's scroll back up really quickly. Yeah, it looks like 3 significant figures. So to 3 significant figures, I actually get 295.84, but I come up with 296 Kelvin to 3 sig figs. Okay? So what we're saying is that we took the metal at 373, mixed it with the water at 293, and the temperature of the water and the mixture, the metal went down from 373 down to 296. And the water went up from 293 to 296. Okay? Does our answer seem okay? Well, certainly the final temperature needs to be between those two temperatures. Okay? Colder object's going to warm up, hotter object's going to cool down. They're going to come to some final temperature together. Now you'll notice that this temperature ends up much closer to the temperature of the water. Why would that be? Okay, well there's two reasons. One, we have more water. We have 50 grams of water versus 20 grams of the metal. That'll make a difference. But what's another thing that would make a difference? Yeah, the specific heat capacity. Water, okay, that water can absorb, look at the difference there, it's more than tenfold. It can absorb more than 10 times more energy per gram than the copper can. Okay? So, it's taking energy from that thermal energy from that copper, that energy of motion, but it's going to take a lot to raise the temperature of the water. It's going to take 10 times more energy than the metal, as the metal loses that energy. And I didn't say that very well, but to get the temperature, say, of water to change 1 degree, that temperature of the metal is going to have to change by 10 degrees. Does that kind of make sense? Specific heat capacity differs by a factor of 10. So it's going to take a lot of energy to raise that temperature of the water. That's why it ends up closer to the water. Wish I had explained that a little bit better, but make sure you note that difference. That's a big difference, over a factor of 10 in the specific heat capacity. Okay, so let's quickly review here. This is an experimental technique, calorimetry. And there's my dog barking. I hope you can't hear that. So here's coffee cup calorimetry. Could do this in the laboratory very easily. We could take that piece of copper metal and heat it up, okay, and then and I think our temperature was 393 Kelvin. Drop it in the water and then measure the temperature change on the thermometer. We could actually run that experiment. Okay, we did the calculation instead. Okay, and again, the key thing is in that calculation, we're going to assume that all the heat lost by the hotter object is gained by that colder object. Okay, and then it just becomes a algebra problem. mcs delta T is equal to negative mcs delta T. This problem we solve for T final. You might get problems where you have to solve for specific heat of maybe, say, an unknown metal. You might have to solve for the mass of a substance. So there's a lot of different variables you could solve for in there. Okay, mass, specific heat, T final, and so on. Okay, I hope this helps. Have a wonderful day. Take care.